Hi, I am Sushma working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering College. In this session, we are going to discuss about the logic gates symbols and truth table. What are the universal logic gates? Why these are called as universal logic gates, and logic gates realization using NAND gates and NOR gates. So, what is logic gate? Logic gates are the basic building blocks of any digital system. So if you want to design any system, any digital system, the basic component we are going to use is the logic gate. Okay, so logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more inputs. So this logic gate contains one or more inputs and it will give the output, one output. Okay. So here the relation between the input and the output is based on certain logic. So that's why these are called as logic gates. Based on this, logic gates are named as AND gate, OR gate, OR NOT gate, XOR gate, XNOR gate. These are the basic logic gates used in the digital system design. So a logic gate is a digital gate that allows data to be transferred. Logic gates use logic to determine whether or not to pass a signal. So here if you want to pass this signal to the output or not, by using the logic, we will implement that gate. So these are called as logic gates. Logic gates on the other hand govern the flow of information based on set of rules. So every gate, suppose we have AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR and XNOR. So these are the basic logic gates we used in the digital system design. Here these gates have some set of rules to pass the output. So it may be these gates maybe have one or two or more inputs but only have the one output for the logic gates. So the following types of logic gates are commonly used in the digital system design. So those are AND, OR, NOT, NOR, NAND, XOR, XNOR. So we will see the what is AND gate function, OR gate function, NOT, NOR, NAND, XOR, XNOR and their truth tables and their symbols for these logic gates. So first we will discuss what is AND gate. An AND gate has a single output and two or more inputs. So the symbol for the AND gate is this one. So this is a 2 input AND gate. A, B, output is Y. Okay. So there may be 2 or more inputs but we will get only one output. Okay. So we can have any number of inputs for the AND gate but output will be the 1. So when all the inputs are 1, whatever we are applying the inputs to the AND gate, if all inputs are 1, you will get the output is 1. Okay. If any one of the input applied to the AND gate is 0, any one input to the AND gate is 0, then output will be 0. Okay. This is main logic behind the AND gate, logic gate. So here the AND gate, if you observe this truth table of the AND gate, here we are taking X and Y as input, Z as output. So this X and Y are input and Z as output. So here in the logic gate, we are applying input either 0 or 1. We can call this 0 is low, 1 is high. So low means here we are applying low voltage, 0 voltage, high means the logic high voltage we are going to apply here. Okay. So if you observe X and Y, both inputs are 0, the output for the AND gate is 0. For X is 0, Y is 0, we are applying X is 0, Y is 0, we are going to get output is 0. If we get apply 0 and 1, we are going to get output is 1, 0, and 1 and 0, 0, and 1 and 1. For the inputs x is 1 and y is 1, we are going to get output is 1. So if you observe this truth table, if both the input x and y is 1, then we are getting output is 1. If any one input is 0, we are getting output is 0. This is basic logic behind the AND gate. And here we can represent this AND gate output z is equal, we can write this is x into y. Okay, so we can write this x into y, x and y. The symbol for AND gate is, we can represent by ampersand x and y. Okay. OR gate. Here for OR gate also, here we can have 2 or more inputs. This is the symbol for OR gate. A, B, only one output y. If we can apply more inputs to the AND gate also, A, B, n inputs, and we can get one output. So the logic here for the AND gate, OR gate is here. If any one of the input is logic high, then we will get the output high. If both the inputs are 0, the output is 0 for the OR gate. So this is the truth table. Truth table for OR gate. So if any one of the input is 1, then we are going to get output is 1. So for both for x and y is 0, 0, we are getting output is 0, and for x and y 0, 1, the output is 1. X is 1 and y is 0, output is 1. X is 1 and y is 1, we are getting output is 1. So here any one of the input is 1, we will get the output is 1. Okay. So here it is like 2 switches are connected in parallel. So here 2 switches x, y, this is z. Okay. 2 switches are connected in the parallel. So for example, x is 0, y is 0. X is 0, y is 0 means here both the switches are open. Okay. So both the switches are open. So there is no voltage applied to this x and y. Then we are getting output is 0 here. Okay. If both x is 0, y is 1. So x is open and y is 1. Okay. So whatever the input we are giving, that will goes to output. So that will be logic high. Then we are going to get the high value. Okay. For x is 1. X is 1. That is nothing but x is closed and y is open, because in that case x is 1, y is 0. X is 1 and y is 0. X is closed switch. If x is 1 means it is closed switch, y is 0 means it is open switch. Then x is 1, y is equal 0. We are going to get output is z is equal 1, because x is closed, whatever voltage we are applying, that will go to the output. And if both inputs are 1, so both switches are closed, then we are going to get output is 1. This case. So for OR gate, both the switches are in parallel, x and y. This is for OR gate. This is for AND gate. B in Z. Here A, X and Y. So for AND gate, both switches are connected like in series. For OR gate, both switches are connected like in parallel. Okay. So this is the basic function behind the OR gate. So here we can represent the function Boolean logic by using OR. So both inputs are x and y. So this we can write OR gate function is x plus y. So the symbol we will represent here plus or we will use here. Okay. Suppose if we have 3 inputs x, A, B, C. Then what is the output here? Z is equal to A plus B plus C. Okay, if we have n inputs, just A plus B plus C plus n. Okay, this is the function of the OR function, OR gate. So NOT gate. NOT gate is a basic one input and one output logic. Here for the AND gate, NOT gate is represented by this symbol. Okay, only it will have only one input. It has only one output. So X is input here, Y is output. Okay, so it is just if we apply 0, the AND gate, NOT gate will go output is 1. If we apply 1, it will give output is 0. So just it will invert the input value and it will give as output. So when the input is 1, the output is 0 and vice versa. So a NOT gate is sometimes called as inverter because it invert the input logic. So 0, if we give 0, it will give 1. If we give 1, it will give output as 0. Okay, this is the truth table for NOT gate. So X is input, Y is output. If we give 0 as input, we are going to get 1 as output. If we give 1 as input to the NOT gate, we are going to get 0 as the output. Another gate is NOR gate. Here we discussed AND, OR and NOT. So these are basic gates. Here we are going to discuss about the NOR gate. In NOR gate, it is sometimes called is not OR gate. Not OR gate. That is nothing but the inverse of the OR gate. So it consists of OR gate followed by a NOT gate. So whatever the logic we have for the OR gate, that should be inverted to the output. So suppose it has AB inputs, Y outputs. So if we by combine these two, we can draw like this. This is NOR gate symbol. AB and Y as output. Okay. So here this is the logic gate symbol for the NOR gate. X and Y input, Z is output. So this we can write as Z is equal X plus Y. We are going to invert the OR gate output. So invert. So invert NOT gate we can apply, suppose X bar. They can write X not X. So these are the NOT gate symbols. Okay. So here we have to invert the OR gate output. Say OR gate is X plus Y. We are inverting that output. So the Boolean statement for NOR gate is Z is equal to X plus Y bar. Since we can write this as X plus Y bars. Okay. That is nothing but NOT of X plus Y. So if we have three inputs, suppose for NOR gate, if we have three inputs, X, Y, Z and P is output. So here P is equal to X plus Y plus Z whole bar. So if we have n inputs, suppose A, B, C are up to n inputs are there, we can apply A plus B plus up to n inputs whole bar. Okay. Here the logic function for the NOR gate truth table is, if we have any one of the input is 1, we are going to get output is 0. If both the inputs are 0 only, if whatever the inputs applied to the NOR gate is 0 or 0, then we are going to get output is 1. So here X and Y are 0, the output is 1. If X is equal 0 and Y is equal 1, the output is 0. If X is equal 1, Y is equal 0, output is 0. X is equal 1 and Y is equal 1, output is 0. So this is the truth table output of the inverse truth table output of the OR gate. Okay, if any one of the input is 1, here we are going to get output as 0 in the NOR gate. NOT gate, NAND gate. NAND gate sometimes is called as, called as not AND gate. So here we AND gate symbol is this one, A, B. Suppose I have Y is equal to Y as output, if directly A into B we will write here. Okay. But for NAND gate, the inverse of the output we have to get in the NAND gate. So NAND gate symbol, the bubble indicates the inverse of the output. So here A, B, here we have Y. So here in this output we have to get the A, B bar because it is equal to the AND followed by the NOT gate, A, B and Y. So AND gate output we are inverting, then that is equal to the NAND gate function. So the symbol for the NAND gate is this one. So if we have 3 input NAND gate, it may be the inputs to the NAND gate is 2 or more inputs we can have, but we have only one output. So suppose A, B, C is input and Y as output. We can write this as A into B into C whole bar. Otherwise A, B, C bar. Okay. So this is a basic NAND gate symbol. And if we go for truth table, in truth table what we will observe here? What are for the different combinations of the input, what is the output? Okay. So here in X and Y, for both, so if we have two inputs, the different combinations we are going to get is 2 square. 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. If we have 3 inputs, the combinations are 2 cube, that is 8. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. A, B, C are inputs. So the 8 combinations we have to run and we have to observe what is the output. Okay. So in NAND gate, if both inputs are 0, then we are going to get output is 1. If any one of the input gate is, if any one of the input to the NAND gate is 0, we are going to get is 1 output. So here any one of the input to the NAND gate is 0, we will get the output is 1. Okay. So if we have both inputs are 1, we are going to get output as 0. So 0, 0, the output is 1. For 0, 1, the output is 1, 1, 0, the output is 1. For 1, 1, the output is 0. Exclusive OR gate. So here the exclusive or XOR gate is digital logic gate that accepts more than 2 inputs, but only one output, one value here. Okay. So the logic symbol for the exclusive OR gate, we can call this as XOR gate. Okay. The logic symbol is, so X, Y as input, Z as output. So here we can write the logic, here is the symbol, logic symbol for the XOR gate is, we can write this one. The logic symbol is this one. So XOR gate represented by sub. So we can write this X XOR Y. XOR gate symbol or this also. Okay. So here the X XOR Y is equal to the X Y bar plus Y X bar. The output is equal to the X Y bar plus Y X bar. So this X bar Y plus X Y bar. Okay. If there are 2 inputs X and Y, Z is the output. So the logic function is X Y bar plus Y X bar. If we observe truth table, this is very, very important. This we will use in the adders, half adder, full adder. There we will see this exclusive OR gate function. Okay. All logic, all combinational circuits will be designed by using only logic gates here. And here, if the both inputs are same, If both inputs are same, then we will get the output is 0. If both the inputs are different values, logic 0 and logic 1, or either logic 1 and logic 0, then we will get the output is 1. So for 0, 0, the output is 0. For 0, 1, the output is 1. For 1, 0, the output is 1. For 1, 1, the output is 0. If you observe, suppose I am taking X and Y as inputs to the exclusive OR gate and Z as output. So we can write this as X XOR Y. So this is equal to X Y bar plus Y X bar. So we have to realize this using gates. What is the equivalent circuit of the XOR gate means? See here, here we know AND is represented by dot and OR is represented by plus symbol and NOT is represented by complement symbol. Okay. So here by using AND or NOT gates, we have to realize XOR gate. So what are the inputs we have? X and Y inputs we have. So the first function in the AND gate is X Y bar. So X we are going to take, and for to get the Y bar, what we have to do? We have to give the input to the NOT gate. So here we are going to get Y bar. Okay. So both are multiplied. So X into Y bar. So the logic gate here we are going to use is AND gate. So X into Y bar we are going to get here. In next function, Y into X bar. So to get X bar, that is nothing, inversion of X, we have to give the X to the NOT gate. So here we are getting X bar and Y. So both are given to the AND gate. Okay. So here Y input to the AND gate is one Y and X bar. So here we are getting X bar and Y. So these two terms are added. So XY bar and YX bar is added. So for plus symbol, we have to use OR gate. So here we are going to get XY bar plus YX bar, that is Z. So this is a exclusive OR gate function using AND and NOR and OR NOT gates. Okay. If we observe exclusive OR gate properties also, suppose we have Z. So A XOR A. A XOR, if we want to convert the exclusive OR gate into NOT gate, okay, what we have to do, okay, and A XOR A and A XOR A bar, A XOR 1, A XOR 0. So here if we know these functions, it will be very easy for the further. So A XOR A. So A XOR A means both inputs are equal to the OR gate, XOR gate. So what is the output? If you observe this truth table, if the both inputs are equal, then output is 0. So X and Y both are 0, the output is 0. X and Y both are 1, output is 0. So if the both inputs are equal to the XOR gate, the output is 0. Okay. And A XOR A bar. So second input is A bar. We are giving A is one input, A bar is another input. Then what is the output? So if the XOR gate has inputs are complemented inputs, so 0 and 1, 1 and 0. So what is the output here? It is 0. It is 1. 0 and 1, 1 and 0, it is 1. So for A and A bar, if A is 1, then automatically A bar will become 0. If A is 0, automatically A bar will become 1. So for both the inputs to the XOR gate are complemented inputs, then we will get the output is 1. And A XOR 1. So in A XOR 1, if we observe A XOR 1, so to convert the XOR gate into NOT gate, we will use this function. Okay, here A XOR 1 will become A bar. So to convert the XOR gate into NOT gate function, so we should make one input is given to 1, another is A, we will get A bar. So if we observe this truth table, if both inputs, suppose both inputs of X is 1, Y we are giving 0, output we are getting inverse of that one. Okay, and Y we are getting, Y is giving 1, we are getting 0. Complement of the Y output, Y input we are getting at the output. Complement of the Y we are getting at the output. So if one input I am making 1, the output we are getting the complement of the another input. So same here, one input for the AND gate, XOR gate is 1, and I am giving A as input, so the output Y is equal A bar. This is a NOT gate function realization. Okay, A XOR 0. If we give A XOR 0, here we are going to get A. So for example, if both inputs are 0, X I am giving 0, Y, whatever Y we are giving, that is passing to the Z, whatever 1 giving, that is passing to the Z. So another input, if A XOR 0 is equal A. So these are basic exclusive OR gate properties. A XOR A is equal to 0, A XOR A bar is equal to 1, A XOR 1 is equal to A bar, A XOR 0 is equal to A. Exclusive NOR gate. So here this is the complement inversion of the NOR gate function, exclusive NOR gate function. So exclusive NOR gate is nothing but the inversion function of the, if we apply NOT gate to the XOR gate, then this is equal to the XNOR gate. So the symbol for the XNOR gate is, just make a bubble for the at the output side for the XOR gate. So here this is the symbol for XNOR gate. Okay, here if you observe the truth table, both the inputs are 0, we will get output is 1. Both inputs are 1, we are going to get output is 1. So if the inputs are complemented inputs to the XNOR gate, we are getting the output is 0. Okay, so for X is 0, Y is 0, we are getting 1 as output. X is 0, for Y is equal, we are getting 0 as output. X is 1 and Y is 0, we are getting 0 as output. For 1, 1, we are getting 1 output. So here for the symbol for the XNOR gate is X NOR Y. For XOR gate, we are using this symbol. For XNOR gate, we are using this symbol. Okay. So the equation for this XNOR function is XY plus X bar Y bar. Okay. In some we can make NOT gate function by using this inversion also. So we can write this as XY plus X bar Y bar. Okay. So how to realize this function using gates? XY plus X bar Y bar. Okay. See here, inputs is X and Y. So these are X dot Y. So the output is given to the X and Y given to the AND gate. And X bar Y bar. To realize to get the X bar, we have to give X to the NOT gate, and Y bar, Y is given to the NOT gates. Here we are getting X bar, Y bar. So both are multiplied, X bar and Y bar. So we have to use AND gate. Both these terms are added. So the first place symbol OR gate. Okay, here we are getting XY, X bar, Y bar. So this is XY plus X bar, Y bar. Okay, so we can write Z is equal X XOR Y, that is X XNOR y bar. Okay, that is equal to xy plus x bar y bar. Okay. So universal logic gates and not set equivalence. So here how to implement gates using only and not gate. Okay. So here for AND gate. Okay. Both the inputs are same. That is A is given to as both the inputs are same. Here also we are getting A. Here also we are getting A. Then it is A into now A, that is nothing but here we are going to get A as output for the AND gate. Both inputs are same. Just it acts like a buffer. Whatever the input we are giving, same output we are getting. Okay, so it acts as a buffer if the both inputs are same. Whatever the input is given to the AND gate, that will be given as output. Otherwise, if we make one input, one of the input is 1, then we are going to get same output, whatever another input is A, so same is given to the output, like buffer. Okay. NAND gate. What is the NAND gate? NAND gate is y is equal A B bar. Complement of AND gate. So, AND gate A into B, if we apply invert NOT gate to the AND gate, so we are going to get A B bar. Now OR gate. OR gate is here A plus B. Okay. So the final output y is equal to A plus B. Here we have to use only AND NOT. But here we have the OR function. So for that we have to use De Morgan's law. So A bar, B bar, whole bar I am applying here. We can write this as A bar into B bar, whole bar. Okay. So here we have AND only NOT gate functions we have. So y is equal A bar. How to implement A bar? A is given to the NOT gate. We are going to get A bar. Another term is B bar. So B is given to the one NOT gate. It is B bar. So these two are multiplied here AND gate. So A bar, B bar is given as input to the AND gate. The output is A bar into B bar. But we have another complement here. So that is A bar, B bar. To get that one, we have to give to the NOT gate. So this is equivalent to the A plus B. Okay. So here by applying De Morgan's law, we can realize the OR function into by using AND and NOT gates only. Okay. NOR gate. We have to implement NOR gate using only AND and NOT logic gates. Okay. So for NOR gate, what is the NOR gate output? A plus B whole bar. So we can write this as A bar into B bar. Okay. So A bar into B bar, A bar. Here we are going to get A bar into B bar. That is equivalent to the A plus B whole bar. And logic gates using only OR and NOT gates only. Okay. Here we have to implement buffer by using OR gate, means both the inputs are same. Then we are going to get a same input as the output. Okay. So here both inputs A and A we are giving. The logic function is A plus A is A. So whatever the input we are giving, we are getting same output like buffer. Otherwise, if we make one input connected to the ground, that is 0, and another input is A, same input is passes to the output. A plus 0 is A. And NOR gate, realize NOR gate is A plus B bar. So NOR OR gate followed by NOT gate is A plus B whole bar. Here we are getting A plus B, and the complement of A plus B is A plus B bar. So that's why we are giving here input to the NOT gate. AND gate. So here A B, we have to get A B. So by using De Morgan's law, we have to use here only OR and NOT gates only. So apply De Morgan's law here. So AB whole bar we can write as A bar plus B bar whole bar. Here we have only plus symbol and inversion symbol, that is OR gate and NOT gates only. So first we have to realize A bar by using NOT gate, here B bar and A bar plus B bar. So plus means OR gate, A bar plus B bar. Okay, we A bar and B bar given to the OR gate, we are going to get A bar plus B bar. Then we have invert that A bar plus B bar. So for that we are giving that to A bar plus B bar to the NOT gate. We are going to get AB as a output. And NAND gate realization using OR and NOT gates only. Okay. So here NAND gate means AB bar. So same as AND gate till here, and we have to get AB bar. So another NOT gate is applied to this realization. Okay. So universal gates. A universal gate is a gate which can implement by any Boolean. We can construct any Boolean function by using these universal logic gates. So we have so many gates, and or not exclusive or exclusive NOR gate, NAND NOR gate. In this we will call only NAND and NOR gates are universal logic gates. Why? Because we can implement any Boolean function using these NAND and NOR gates compared with other gates. Okay. So here NAND and NOR gates are universal logic gates. In practice, this is advantageous since NAND and NOR gates are economical and easier to fabricate, or the basic logic is in all IC digital logic families. Okay. In fact, an AND gate is typically implemented as NAND gate followed by an inverter, not to the other way around. Likewise, OR gate is typically implemented as NOR gate followed by an inverter, not the other way around. So here any logic function, any Boolean function can be implemented by using these universal logic gates that are NAND and NOR gates. So implementing AND or NOT gates using only NAND gates. So here we can implement AND function or NOT, NOR, exclusive OR and exclusive NOR. So all these logic gates by using NAND gates. So here NAND gate symbol is represented as this one, A, B, and here we take it as a Q or Z, anything we can take here. So here we represented A, B and Q as output. Okay. To convert the NAND gate into inverter, just if both the inputs are given same input, then output is inversion of the input. Okay. So here A we given. So Y is equal A into A bar. A into A is equal to A. So A bar. And if we construct AND gate using NAND gate, here see, here finally we have to get NAND gate function A into B. Okay. So A comma B, A and B given to the NAND gate. A into B bar we got. So to get the AND gate we should get AB. So again we invert that AB bar by then we will get the AB. So by using NAND gate to get the NOT gate function, so we have to use this function. So both the inputs are same. Here AB bar, here both inputs are same. Then we are getting the inversion. So A, B we will get. Okay. And buffer. So if the buffer, whatever the input is given, the same should pass to the output. So A is given to the one NOT gate. We are getting A bar. Again A bar is passed through the another NOT gate, we are getting A. And OR gate is A plus B. Okay, so A plus B means we have to realize that one using NAND gates. So A plus B whole bar, De Morgan's law, apply De Morgan's law. Here A bar into B bar whole bar. So A bar we have to realize using NAND gate, and B bar also using NAND gate, and both function using this A bar dot B bar whole bar using NAND gate. So A bar, to get A bar by using NAND gate means both the inputs are same to the NAND gate, it will act as a NOT gate. So this is A we are giving, A bar we are getting, B bar we are getting. So A bar dot B bar whole bar, that is given to the NAND gate, we are going to get OR gate output. For exclusive OR gate, the final function for the exclusive OR gate is AB bar plus AB whole bar. So here Q is AB bar plus A bar B. Final we have to get the AB bar plus A bar B. See here we are giving A and B. This is first gate, second gate, third and fourth. Okay. For first NAND gate, here we are going to get AB bar, and for second gate, one input is AB bar, another input is giving from A. For third NAND gate, here we are getting one input is B, another is AB bar. Okay. So here this NAND gate, A into AB bar whole bar, this B into AB bar whole bar. So if we see A into AB bar, this is equal to the A into A bar plus B bar. A into A bar is 0, A B bar we are going to get here. This is AB bar and whole bar we have. So A B bar whole bar, and another one is equal to B into A bar B, AB bar. So De Morgan's law is AB bar is equal to A bar plus B bar. Okay, B into B bar is 0. Here we are going to get B into A bar. And we have another invert symbol. So here both the inputs here we are getting A B bar whole bar and B A bar whole bar. Okay, so here A B bar whole bar plus B A bar whole bar, it is NAND gate function. So we will get inversion of that one. Okay, into. So this is equal to the AB bar plus BA bar. So we have to realize the each Boolean equation, what are the we are giving as input, and we have to realize using NAND gate realization, and finally we will get here exclusive OR gate function. For NOR gate also here same function, we have to give the output to the NAND gate. Then we will get this OR gate, same function. We are giving this output to the only refers with the NOT gate. The OR gate is output is followed by NOT gate. We will get the NOR gate. Here also same. Here the exclusive OR gate output is given to the NOT gate. Then we will get the exclusive NOR gate. Otherwise, we can realize this function by using, here we have to get AB plus A bar B bar. We have to get. So implementing AND or NOT gates using NOR gate. Okay. So here NOR gate symbol is this one. So A, B, we are going to get A plus B whole bar. So if we both to convert the NOR gate into NOT gate, just give both the inputs are same, then we will convert the NOR gate into NOT gate. Okay. So OR gate means it is NOR gate output is given followed by NOT gate, then automatically we will get the OR gate output. So OR gate is followed by NOT gate using NOR. We are going to get OR function. Buffer means whatever the input we are giving, same output we have to get. So here NOT gate using NOR is followed by another NOT gate. Then we will get the output. And AND gate. So here in AND gate we have to get A dot B. So A dot B means by using De Morgan's law, here we have to use only NOR function. So apply De Morgan's law here, double complement, because AB bar, whole bar is same as AB. So if you apply De Morgan's law, so this one A bar B bar plus whole bar. So realize A bar using NOR, B bar using NOR, and apply it to the NOR gate. So A bar, this is both inputs are given same. So we are getting A bar. Here both inputs are B. We are getting B bar. So A bar, B bar is given to the NOR gate. Here we are going to get AB output, AND gate output. So exclusive OR gate. Okay. So here we are getting A, B. Here both inputs are same. So A bar, B bar. So here we are getting A plus B whole bar. And here A bar plus B bar whole bar is equal to AB. So then here if we realize this one, we will get A bar B plus A B bar. Okay. Here also same for exclusive NOR gate. Here A plus B whole bar and B is given to the NOR gate. A plus B whole bar. Here A is given. Here B is given. So here A plus B whole bar is equal to the A bar B. Here A plus B whole bar plus B whole bar is equal to the AB bar is given to the NAND gate. So here A bar B plus AB bar whole bar, that is exclusive OR function inversion, is equal to the AB plus A bar B bar. Okay. Here for NAND gate, the NAND gate same. This is NAND gate realization. AND gate is followed by NOT gate. Inversion of AND gate output is equal to the NAND gate. So what is the use of logic gates? Logic gates are utilized in variety of technologies. These are components of chip, which are components of computer, phones, laptops. If any digital system, the basic system will be realized by using logic gates. Okay. So logic gates may be combined in a variety of ways. Millions of these combinations are necessary to make newest gadgets, satellites, and even robots in every household items, digital electronic applications. We will use ICs. So in IC, if we design any IC, the basic system will be realized by designed by the logic gates. Okay, these logic gates will be realized using transistors. Okay, so the simple logic gate combinations can also be found in burglar alarms, buzzers, switches, street lights. These all are the applications of the digital system applications. So in every digital system applications, we will realize the design by using logic gates. So logic gates are also important in data transport, calculation, and data processing. Even transistor logic, that is TTL and CMOS circuitry, make extensive use of logic gates. So here we will see simple Boolean expression. We will take and how to realize this Boolean expression using gates. See here, y is equal to AB bar plus C bar. So here we have AB bar and C. So A dot, we have to realize if any two we are multiplied or it is represented by dot symbol, we have to use AND gate. A dot B. Okay. If it is OR gate, we will get plus symbol. For NOT gate, we will get the complement. Okay. This also we will realize. Okay. So here C, A, B bar. First take this term A, B bar, literal A, B bar. So to realize B bar, we have B input. To get B bar, first we have give B input to the NOT gate. We will get the B bar. Okay. And A into B bar. Into means A, B bar means here we have to take the AND gate. So A, B bar is given to the AND gate. We will get the A, B bar. Okay. And this A, B bar is added to the C. So A, B bar is plus symbol. So we are adding it to the C. Then A, B bar plus C we are going to get here. Okay. See here A into C plus D whole bar plus B. Here how many inputs we have? A, B, C, D, E. Okay. Take first term and second term. Okay. First A into C plus D whole bar we will realize first one. So here what we have here? C plus D. A, C, D. C plus D. Plus means what we have to do? Which gate we have to take? OR gate. So here we are getting C plus D. Then it is multiplied by the A. So then we have to give that to the AND gate. So it is A into C plus D. Okay. But we have to get the complement of that one. Either use NOT gate here. Otherwise directly we can give this to the NAND gate. AND plus NOT is NAND gate. So here directly we can draw NAND gate. Okay. Second term is here we got the A into C plus D whole bar. Second term B into E. So B and E. Here both are multiplied. So use AND gate. These two terms are added here using plus symbol. So take B OR gate. So this is final output Y. So we have to observe which gates we are using to realize the Boolean expression. Suppose if you want to take the Boolean expression in truth table and realization using logic gates, here this is the Boolean expression A plus B into B bar plus C here. In this table we have 3 inputs A, B, C. So for 3 inputs how many combinations we will get? 2 cube, that is 8 combinations we will get for the input. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So take A plus C as one term, B bar plus C as one term, the total term Y is output. So A plus C, A 0 plus 0, 0. And B bar plus C, B bar is 1 and C is 0, 1. So we have to realize each function and finally we have to observe the output. Okay. And if we see this realization A plus C into B bar plus C. So A plus C. So take A, B and C. Okay. So for A plus C. So plus means we have to take the OR gate. Here we are getting A plus C. But in second term we have B bar. So B bar plus C. B bar plus C means here we are getting B bar. B is given to the NOT gate. We are getting B bar. And to get the B bar plus C, we are giving that to the OR gate. Here we are getting B bar plus C. Then both A plus C and B bar plus C are multiplied. So then we have to use the AND gate. So here A plus C and B bar C is multiplied. That is our final output. Okay. So these are the basic logic gates and universal gates and realization of all logic gates using NAND and NOR and basic Boolean expression realization using logic gates. So here whatever the figures are taken from the electronics tutorials .ws and the topic we can read from the Modern Digital Electronics and Digital Design Principles and Practices. In every digital system design books, we will see the basic logic gates, functions and truth tables and their symbols. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.